Okay, thank you. So here I want to talk about a coupled modeling system. So we have developed in recent years. So there's increasing demand on seasonal Arctic sea ice prediction, but it's still very challenging. So we already know that. So this one, so this is the predicted September Arctic sea ice extent by all dynamic models. Here we talk about a dynamic model, okay? So no statistic model. So from the sea ice outlook, here the blue circle is the prediction from July outlook. And the right square, so is satellite observation. So you see for most years, the prediction deviates from the observation significantly. Especially you see the last year, probably also this year. So, and as I mentioned, so recently, so we have developed a couple of modeling system. So for this seasonal Arctic sea ice and climate prediction, so we want this modeling system so have sufficient flexibility. Flexibility means each model component has different physics option to choose, and also the capacity to integrate, ongoing improvement. So we couple the CIS model with WOLF and RAMS model within this coast modeling framework. Okay, so So this is basically the major physical parameterization used in our modeling system. So just list here, and also we use the NSAP CFS seasonal forecast as a boundary condition. And a good prediction system also need a good data assimilation system. So we implemented this parallel data assimilation framework in our modeling system. Specifically, we use this local area subspace transform Kalman filter to assimilate satellite derived CS parameters, ice concentration from SSMISS, and ice thickness from a combination of cryoside 2 and smalls. And we know the cryoside 2 and smalls ice thickness are only available until April, okay? And so we use daily Pell mass as a real analysis to calculate the climatology of ice thickness evolution, and then apply it to satellite ice thickness to estimate the ice thickness on the date of model initialization, okay? And so now let's take a look at our prediction experiment. So first, the July outlook for 2017. And so this is the CS initial condition. So after data assimilation, so you see the spatial distribution of ice concentration thickness. So they're comparable to the observation. So this column. So compared to this no data assimilation. And so this is the predicted total Arctic CS extent from July to September. And the black line is satellite observation, and the black line is satellite observation. The blue line is our prediction. So basically, our prediction captures observed evolution, and also is better than DAM prediction for most of the time. Okay, and the spatial distribution, ice concentration. So July, August, September, our prediction. So they're broadly consistent with the observation, except so our prediction shows a slower ice retreat in the Pacific sector. So you can see that. And so this is 2018, so July and August outlook. So again, so similar to the observation, better than the DAM prediction. And for this year, so we also conducted extended prediction. So from July to January next year. And you can see the blue line is our prediction, so black observation. And the dashed line is the DAM prediction. So our prediction also is better than DAM prediction until early December, so show this extended predictive scale. And to understand the influence of data assimilation on seasonal Arctic sea ice prediction, so we conducted the experiment with direct insert of satellite observation. And here, again, black line observation. And the blue line, so no data of simulation. So you see the no data of simulation significantly overestimate the S10. So directly inserting satellite ice concentration. So we have this yellow line, okay? So closer to the observation, but the improvement disappears after a few weeks integration, model integration, okay? And so by contrast, directly inserting satellite ice concentration and thickness, we end up with this red line. So underestimate the observation. So assimilating both satellite ice concentration and thickness, so you see we have the best predictive skill, okay? So that's that line, close to the black line. And also, we compare the difference between assimilating satellite ice concentration, ice thickness, sorry, and also the pile mass ice thickness in our modeling system. And with this is the RMSE relative to the observation. And the solid line is our prediction, and not our the prediction assimilating satellite ice thickness, and dashed line assimilating pile mass ice thickness. So you can see, so basically, so they have a comparable and a small RMSE at the beginning, but after that, so assimilating pile mass ice thickness has much larger MSE compared to assimilating satellite ice thickness. So this suggests assimilating satellite ice thickness so can promote the predictive skill, okay? And so this is 2020, I'm not going to talk about this, but for this year, so we pull out the best and worst ensemble member. So we compare the surface wind, you know, the difference between this best and worst ensemble member, and now with this, July and August. So you can see, so there's anomaly cyclonic circulation, so in the Central Arctic, so which sweeps the hot air, you know, anomalous hot air from Siberia into the Central Arctic, so influencing the ice evolution. So this suggests, you know, the better prediction of atmospheric circulation, so promoting, you know, the ice prediction skill, okay? And also in the past 2 years, so we have made a substantial model improvement. So just one example, for example, this is the surface air temperature. And so you see the middle row, so the old version, our old version, so has this cold bias. So in much of the model domain, but with the improved convection and boundary scheme, we end up with the bottom row. So warmer state, that means reduce the cold bias. And so it's also true for sea surface temperature. So the middle column, so we see the cold bias. So for Pacific, Atlantic, so this is the old version. So the new version, so with the improved advection scheme, not improved, so the change of the advection scheme to reduce this numerical oscillation, we end up with this column. So warmer state, so reduce the cold bias, okay? And because of this improvement, so we end up with this. You see the old version, improved version, so this is the predicted IC10. So you see the improved version corrected, so this delayed ice recover issue in the old version in late September. So finally, so we add the wave model in our modeling system, so it's a SWAN, and to realize this wave ice interaction, two-way interaction. And to realize this two-way interaction, so we implemented this new flow size and also lateral melting scheme. So in CS model, you know, to realize this coupling, okay, between wave and ice. Just a little bit of result. So this is for this year, prediction for this year, 2022, and this predicted flow size for September. So you see the large flow size, so in the Canadian Arctic, and small, very small, around 5-10 meters, so in the rest region. And this is the analysis of sea ice mass budget. So here you just need to focus the purple line, okay? And so the left one, so no wave ice interaction. The right one, with wave ice interaction. You can see, so with the wave ice interaction, so the lateral melting is greatly enhanced, okay? Because of this, so we see this, so this is a difference in CS concentration between waves and without wave. So the wave ice interaction produces this less ice is in this marginal ice zone, so Siberia and Atlantic, Pacific, and more, more sea ice in the Canadian Arctic. So this is just a preliminary result, okay? Okay, so this is my summary. I'll leave my summary here, so for questions. Okay, thank you.
Okay, so we have time for questions. Yes, Johnny.
Yeah, it's really nice to see this interaction with the waves in this animation. In the time series, it looked like the lateral melting, which included the lateral melting. It looked like there was less basal melting. Is that?
Yeah.
Is there some sort of compensation there going on, or is that, or is it?
Yeah. So there's
retuning.
Yeah, you're right. So there's a compensation. So first we see this enhanced lateral melting, but also we see this reduced bottom melting. Okay. So you're right. So there's a compensating, but enhanced lateral melting, so slightly exceeds this reduced bottom melt. Yeah. So based on our CS mass bar data analysis. Yeah, you're right. Yeah.
I have a quick question about the advection schemes. What was the deficiencies of MP data, and how was it improved with the schemes, the new schemes that you used?
So sorry. Yeah. Oh, how to? Anyway. Yeah. So basically, we just changed the advection scheme to reduce this numerical oscillation, and yeah, here. So. For your information, so we changed this MP data to this 3 order. Okay, yeah.
Where is the oscillation?
Oscillation. Yeah. So we plot this vertical profile of temperature and the salinity. So in the Arctic Ocean, we can see this grayscale oscillation. So but not in sea surface temperature. Okay. Yeah. So we see this reduced oscillation. Yeah.
Okay. Thank you. Last question, maybe? No? No? Okay, so